All right, so good morning again, guys. Now that the recording started, we can go ahead and jump on in to the wonderful world of heat transfer. Where previously on Dragon Ball, we were talking about condensation heat transfer. And so when it comes to condensation heat transfer, we were looking at plates and tubes, which makes me feel like this is a Joe Dirt's Snakes and Sparklers, but here we are, where we can have condensation on a vertical plate, an inclined plate, horizontal plate, or something more useful, the outside or inside of a tube. And because drawings are important, we're going to say, we can have condensation of some form around these surfaces, right? And we stated that the flow regime is important or strongly influences our heat transfer. Or I should say heat transfer rate. Where we stated we have Q is equal to H, A sub S, Tsat minus Ts, because since we're looking at condensation heat transfer, the surface temperature is below the saturation temperature, which is what allows the vapor to condense. That also is equal to the condensate rate times our modified enthalpy of vaporization, where lambda star is lambda plus 0.68 times the heat capacity of the liquid times our saturation temperature minus our surface temperature. And that accounts for the subcooling that is experienced by the fluid as it flows off the plates and off the tube. And so based on the flow regime, we had laminar, wavy laminar, bilaise, and turbulent. Where laminar was a Reynolds number below 30, wavy laminar was between 30 and 1800, and turbulent was considered anything above 1800. And so from this, we had a few expressions, keeping in mind that if we know the thickness of that film layer, we can calculate our Reynolds number as the density of the liquid, the velocity of the liquid as it flows, times our thickness over our viscosity. And if we wanted to, we can also describe it as a function of mass flow rate, because that's a good way to check everything. As 4 times our mass flow rate. Now there's a 4 here. Yes. Over the wetted perimeter times viscosity of our liquid. However, most of the time, we do not know our delta, our film layer thickness. And so we have to rely on Reynolds number expressions in these regimes to kind of indicate to us what type of film flow we should expect in our system. And so just to kind of revisit all of these expressions for laminar on a vertical plate, if I can find the right page. It's always at the bottom. We could say our heat transfer coefficient is 0.9343 times gravity, density of the liquid minus density of the vapor, times our lambda star, thermal conductivity cubed over viscosity of our liquid times Tsat minus Ts times the height of the plate, which this text I'm using uses L because it thinks it's funny, in units of watts per meter squared Kelvin. Now, one thing I do want to point out, because I believe I unfortunately made an error last Monday, so feel free to get out your torches and pitchforks, and that I may have missed the cube on the thermal conductivity of the liquid. So please make sure that you do this. This should be cubed. This should be here. So please double check your notes from Monday, and if I left that off, add those to your notes. I'm gonna double check after class the notes I post on Blackboard and re-upload them.
Is that for both vertical and horizontal tubes?
Yeah, all of these follow this form, and so I'm gonna go over them right now, but in most of these, when that thermal conductivity in the liquid's in the numerator, it should be cubed. All right, and we can also say for laminar, which is Reynolds number less than 30. We can also say our heat transfer coefficient is, for the vertical plate, as 1.47 thermal conductivity of our liquid times Reynolds number to the negative 1/3 times our G over kinematic viscosity of the liquid squared to the 1/3. And this is our Greek nu kinematic viscosity. And so for wavy laminar, which I should call wacky inflatable arm flailing laminar, is Reynolds number times thermal conductivity of the liquid divided by 1.08 times Reynolds number to the 1.22 minus 5.2 times our gravity over kinematic viscosity of the liquid squared to the 1/3. And this thermal conductivity is to the power of 1, so this is correct. We can also solve and confirm our wavy laminar Reynolds number using this expression, which is equal to 4.81 plus 3.70 times length times thermal conductivity of our liquid times Tsat minus Ts divided by viscosity of our liquid times lambda star times our gravity over kinematic viscosity term, and this is all to the 0.82 power. For turbulent flow, we can calculate our heat transfer coefficient. Here, I'll scroll up so you guys can see. Actually, I'll just zoom. H turbulent for a plate is going to be Reynolds number times thermal conductivity of a liquid divided by 8,750 plus 58 times the Prandtl number to the negative 0.5 times the quantity Reynolds number to the 0.75 minus 253 times gravity over kinematic viscosity of the liquid squared to the 1/3. And we can calculate the Reynolds number in our turbulent system. As giant expression, 0.069 times length times thermal conductivity of the liquid times Prandtl number to the 0.5 times Tsat minus Ts divided by viscosity of the liquid, thermal conductivity of the liquid. Oh, sorry, lambda star. That didn't make sense. Times gravity over kinematic viscosity of the liquid squared to the 1/3 minus 151 times Prandtl to the 0.5 plus 253. All to, which power is this? 4/3 power. So a lot of these systems, what you have to do is you have to guess whether it's laminar or turbulent flow, solve for the Reynolds number. So probably using vert wavy or this vert turbulent if you think it's going to be one or the other. Then that will tell you whether you're right or not. And based on the Reynolds number, you solve for the heat transfer coefficient and then eventually the heat transfer rate.
Is the exponent on that very, oh, thank you.
That help?
Yes, the 3 was cut out of the screen.
Sorry, my bad. All right.
Is that, what is that value next to the PR to the 0.5?
It is 151 times Prandtl number to the 0.5.
Okay, thank you.
You are welcome. And once again, as we talked about inclined plates, where H inclined was simply H vert times cosine of theta. All right, and I think this is about where we left off, where now we can kind of look at tubes and tube banks. Or I should, to make this neater, say condensation on tubes and tube banks. So when we have condensation on the tubes, H on a tube, and this is assuming it's horizontal, our expression is 0.729 gravity, density of the liquid minus density of the vapor times thermal conductivity of the liquid cubed divided by viscosity of our liquid times temperature of the saturation minus the surface temperature times the tube diameter, all to the 1/4 power. And for a vertical tube, our H horizontal times 1.29, diameter of the tube over the length of the tube to the 1/4 power. All right, so quick break from alphabet soup. So which orientation will result in a higher heat transfer coefficient?
it depends.
Wouldn't it depend on diameter and length of the tube?
You guys are too smart. It does depend. Yeah, from this equation, if we set h vertical equal to h horizontal, that gives us a solution of the length equaling 2.77 times the diameter. Which means if the length is larger than essentially 3 times the diameter, you're going to get a higher overall heat transfer coefficient and heat transfer rate if the tube is horizontal. If you have a really short tube, not really sure why, then you'd have a better system if it's in a vertical orientation. But in general, horizontal is desired. That's why most shell and tube heat exchangers have tubes horizontally, especially when you have a phase change. So now let's talk about condensation on tube banks. i.e. shell and tube heat exchanger. Right, so if we're condensing something in the shell side of a shell and tube heat exchanger, what we're gonna have is, our tubes in some sort of order, and condensation kind of around these tubes. And what we find is that the tubes on the top of our shell and tube heat exchanger is going to influence the film thickness and condensation rate of tubes underneath it. Right, we kind of have this waterfall effect. Which means we have to identify a correction factor for a heat transfer coefficient to kind of describe the average performance of each single tube. And so the way we can do this is through a correction that states the heat transfer coefficient on a tube in a tube bank, where I can say sub n is equal to 1 over n to the 1/4 times the heat transfer coefficient of one tube, where n is the number of tubes in a column. So, kind of what I'm showing here, where I have 8 tubes, my n would be 2, because I have kind of 2 tubes in this column, or number of rows, if you'd rather think of it that way. And I can also combine it with my original expression and just say for a tube bank, my heat transfer coefficient is going to be 0.729 times G times rho L times rho L minus rho V, K sub L cubed, viscosity of the liquid, T sat minus Ts times N times D, all to the 1/4. Oh, and I forgot the lambda star. Make sure I didn't forget it up there, because there's probably a good chance I did. So this goes here. It goes here too. All right, so that kind of wraps up looking at condensation heat transfer rates on tubes and on tube banks. Now, there is an expression for heat transfer coefficients within a tube. It looks kind of like this, but I would argue that's probably not going to be the most efficient use of a heat exchanger. in that you're going to have less surface area for condensation, and there's no real place to go as the material condensates, right? Because over time, if you're condensating inside the tube, you're eventually going to have a film take up the entire interior of the tube, which means you're going to have more and more heat transfer resistance associated with the phase change. And I can kind of see if I can zoom in over here and share you this PDF. So, you know, as you see, if you have condensate flow inside a tube, eventually this liquid is gonna just exist entirely within the tube. But that film thickness is gonna get higher and higher. And you're gonna have such a great heat transfer resistance for that phase change. This is gonna be wildly inefficient as compared to condensation on the outside of a tube. So that's why, even though we have this equation, it's on the selection notes to let you know it's there, I wouldn't recommend setting up your system to condense within a tube. So any questions on heat transfer by condensation? Like I said, I know it's some alphabet soup. I want to spend the rest of class kind of going over a couple examples to kind of give you some more some practice and application of some of this. But are there any questions about the concepts, the equations, or how to approach these problems? All right. If not, let's take a look at this example, example 2, where it states that saturated steam and atmospheric pressure is going to condense on a 2-meter high by 3-meter wide vertical plate maintained at 80 degrees Celsius. Estimate the rate of heat transfer via condensation onto the plate, as well as the condensation rate of our steam as it drips off the bottom of the plate. Okay. Let's go back to our notes and we'll see what we can do about this example. So we're going to say example condensing on vertical plate. So if I wanted to draw it, I have a plate and I've got condensation, some thickness, I have no idea. And then I have some sort of M condensation, the temperature of my steam, it's at saturation, it's at atmospheric pressure. So I say it's 100 degrees Celsius. The surface temperature of the plate is maintained at 80 degrees Celsius. And to identify the solution for this problem, I'm going to need to know quite a bit about steam at atmospheric pressure and 100 degrees Celsius. So from the Google, density of my liquid is approximately 965 kilograms per cubic meter. The heat capacity of my liquid is approximately 4206 joules per kilogram Kelvin. Viscosity of my liquid is approximately 0.315 times 10 to the minus 3 kilograms per meter second, or 0.315 centipoise. The thermal conductivity of our liquid is approximately 0.675 watts per meter Kelvin. What else do I need? And if I wanted to find the kinematic viscosity, which I'll need, I take my viscosity, divide it by my density, and I get about 0.326. times 10 to the minus 6 meter squared per second. Let's see if there's anything else I need. I need my latent heat of vaporization. Which should be 2257 kilojoules per kilogram. And so one question that you may have is, well, what's the best temperature to get these properties at? Because we're looking at mainly liquid properties. We know the vapor's at 100 degrees C, it's condensing, and the plate's at 80 degrees. And I've stated that the liquid will essentially cool below the saturation temperature. So if you want, for good measure, you can probably find these properties, where T is about 90 degrees C. You can kind of try to find an average. If you have a really large temperature gradient between Tsat and T sub S, I would maybe lean a little closer to Tsat depending on the size of the plate. So is this going to be an exact science? No. But like I said, we're trying to make reasonable estimations of what we can anticipate in a real process.
What's the density of the vapor? Because I think we need that one as well.
When we look through these calculations, we might be able to get away with not needing it. In this example. But if you want, I can say the density of the vapor. I don't have it in my notes. I'm actually going to have to go to the Google ALA Engineering Toolbox Steam tables.
Sorry, I thought we needed it.
Let's see. Yeah, I don't think we need it. I don't want to waste too much time digging this, looking for it.
Okay.
So if you want, I'll just say it's 0.7 kilograms per cubic meter. If you guys want to challenge me on that, go for it. So we know our condensation rate can be described by Newton's law of cooling, as well as by thermodynamics, which tells us that we have m lambda, but we're sep cooling, so we really need m lambda star. So probably the first thing we can identify is our modified latent heat of vaporization, because it's a good way to get some points on things. So I can say lambda plus 0.68 times heat capacity of our liquid times Tsat minus Ts, which is equal to, as I stated, 2257 kilojoules per kilogram Kelvin plus 0.68 times the heat capacity of our liquid, which I had stated earlier, was about 4206, or I can say 4.206 kilojoules per kilogram Kelvin. This is per kilogram, units are important, times 20 Kelvin, because 100 minus 80 is 20. This gives us a modified latent heat of vaporization of approximately 2,314 kilojoules per kilogram. Not a large increase, but a significant one. So, as we don't know what the Reynolds number is, we really can't find our heat transfer coefficient, because as we found with our adventures in alphabet soup land, H is strongly going to be dependent on that Reynolds number in that flow regime. So we kind of have to make an assumption and an educated guess as to what the Reynolds number would be. I'm going to start and assume the system is wavy laminar, and calculate the Reynolds number for that wavy laminar by the expression that I had previously, which was 4.81 plus 3.70 times the length or height of the plate, which it's 2 meters high in this problem, times the thermal conductivity of our liquid, which I stated was approximately 0.675 watts per meter Kelvin, times Tsat minus Ts, which is 20 Kelvin, divided by the viscosity of our liquid, which we had as 0.315 times 10 to the minus 3 kilograms per meter second, times modified latent heat of vaporization, or 2314 times 10 to the third joules, because I need it all in the right kind of units per kilogram. And this is going to be times that G over kinematic viscosity term, or 9.81 meters per second squared, divided by our kinematic viscosity of 0.326 times 10 to the minus 6 meters squared per second squared to the 1/3, all to the 0.82 power. So if we do that, because we have the technology, we can find that our Reynolds number is approximately 1,290, which is wavy laminar. So yay, good assumptions through the power of hindsight. So wavy laminar is correct. So with this Reynolds number in hand and confirming that it's wavy laminar, I can now solve for our heat transfer coefficient using our wavy equation as the Reynolds number, or 1,290 times the thermal conductivity, 0.675 watts per meter Kelvin, divided by 1.08 times our Reynolds, 1290 to the negative 0.5, minus 5.2 times our gravity thing, 9.81 meters per second squared, divided by the kinematic viscosity squared, all to the 1/3 power. So if we plug this in, we get a heat transfer coefficient of approximately 5,850 watts per meter squared Kelvin. So once again, we get to spend the majority of the problem finding our heat transfer coefficient. The good news is now that we have our heat transfer coefficient, we can solve for our heat transfer rate as H, 5,850 watts per meter squared Kelvin, times the surface area of our 2 meter by 3 meter plate. So it's really just 6 square meters times our Tsat minus Ts, or 20 Kelvin. We do this and we get a Q value of approximately 702 kilowatts. And with this in mind, I know that Q also equals m dot lambda star, which implies that our m is going to be equal to 702 kilowatts divided by our 20, what did we have? 2314 kilowatts per kilogram, which gives us a condensation rate of approximately 0.3 kilograms per second.
Dr. Lopez,
Yes.
if you had kilowatts on the top and the bottom, wouldn't that second go away?
Ah, you're right. It's kilojoules per kilogram. Thank you. Units are important. -1, Dr. Lopez. So any questions on that problem? You guys kind of follow the process. All right, let's see if we have time for one more problem, looking at tubes and a tube bank. So for this problem, we're going to say the condenser of a steam power plant operates at a pressure of 7.38 kilopascals. At this pressure, steam is going to condense on the outer surface of a horizontal pipe at 40 degrees C, which is maintained at a surface temperature of 30 degrees C by cooling water. And if the outer diameter of the pipe is 3 centimeters, what is the rate of heat transfer to the cooling water and the condensation rate of steam? Assuming we're just going to look at a single horizontal pipe, and we're using a basis of a unit length, or assuming the pipe length is 1 meter. All right, so for this, we would have to find the steam property somewhere between 40 degrees and 30 degrees, 35 degrees. So from a steam table, after I switch it back to our notes, say condensing on a pipe. We need steam at Tsat, or T about 35 degrees C. So what I have is the liquid density. It's about 994 kilograms per cubic meter. For this, we do need a vapor density, which is about 0.05 kilograms per cubic meter. The enthalpy of vaporization, lambda, is 2407 kilojoules per kilogram. The heat capacity is approximately 4178 joules per kilogram Kelvin. The viscosity, is 0.72 times 10 to the minus 3 kilograms per meter second. And the thermal conductivity, I think this was the last one we need, is 0.623 watts per meter Kelvin. All right, so for this problem, all we really need to calculate before we can do this is our modified latent heat of vaporization. So lambda star is going to be equal to 2407 kilojoules per kilogram plus 0.68 times 4.178 kilojoules per kilogram Kelvin times our Tsat minus Ts, which is 10 degrees C. Because once again, we're looking at a Tsat of 40 degrees and a surface temperature of 30 degrees. So with this, I can solve for H of my tube as R 0.729 times gravity of 9.81 meters per second squared times the density of our liquid, 994 kilograms per cubic meter, times the density of our liquid minus vapor, or 994 minus 0.05 kilograms per cubic meter, times the thermal conductivity cubed, or 0.623 watts per meter Kelvin cubed, times our modified latent heat of vaporization, which I actually didn't solve. I apologize. It ends up being 2435 kilojoules per kilogram. So if I put it in terms of joules, 2435 times 10 to the third joules per kilogram. All of that divided by our viscosity of 0.72 times 10 to the minus 3 kilograms per meter second times our Tsat minus Ts, 10 Kelvin times our diameter, 0.03 meters. All of that to the 1/4 power. So it's just a giant, plug and chug type problem. You do it, you end up with an H value of approximately 9,290 watts per meter squared Kelvin. And so with that, we can solve for our Q. If my pen will work. The only thing we need is our surface area. We're doing this per unit length, as we said. So we have pi times 0.03 meters times 1 meter of length, which gives us a surface area of about 0.094 square meters, which makes Q 9,290 watts per meter squared Kelvin times 0.094 meter squared times 10 degrees Kelvin, which gives us a heat transfer rate of approximately 8,760 watts, which, as I stated in our previous problem, is equal to m dot lambda star, which implies m dot is equal to 8,760 watts divided by R 240, 2435 times 10 to the third joules per kilogram, which gives us our answer in kilograms per second as something very, very small, 0.0036. Which means if we wanted to have an appreciable condensation rate, we might have to look at a system with tube banks.
When you got the density of your vapor, did you use at the pressure of 7.38 kilopascals?
Yes, which is why the density is so low. So any questions on this? All right, so I know we're out of time. One thing I would say is, if we wanted to up this condensation rate, we can consider the use of a tube bank. Where, let's say if we had 12 tubes in this kind of pattern, to modify our solution, all we would have to do is solve for our new H, which is going to be 1/3 to the 1/4 power times our 9,290 watts per meter squared Kelvin, which doing that, we get a value of about 7,060 watts per meter squared Kelvin. And then for our heat transfer rate, what we would do is up our surface area by 12, because now we have 12 tubes, which would give us a surface area of approximately 1.13 square meters. And then resolving our Q, we would see a marked increase in our heat transfer rate, right? Because we have more tubes. And so for this system, our Q would be close to about 79,850 watts, which would make our condensation rate about 0.033 kilograms per second. And so just to kind of give you this last minute rundown, it's to illustrate that when we have multiple tubes and existing in a tube bank, our heat transfer coefficient does decrease because now we're looking at the influence of the tubes above as they influence the tubes below. So the heat transfer coefficient does fall, but we have a greater surface area, which is a larger contributor to our anticipated heat transfer rate and our condensation rate. So it's just a quick illustration of how we can incorporate those considerations of tube banks into these calculations. So that about wraps it up for condensation. I think on Friday we'll jump into going over some radiation heat transfer stuff. We'll try to finish it. We'll see how it goes. And then next Monday we will do a final course review and wrap up. So any last minute burning questions? I'd be more than happy to answer. If not, I thank you guys for your attention, and I appreciate your patience as we kind of trudge through a lot of these equations. I know they come off a little complicated, but you'll find the actual execution of these problems are pretty straightforward. It's really just finding the properties at the right temperature and plugging them into the appropriate equation. It's a lot less of an existential crisis like fluid mechanics, that's for sure. All right. If not, thank you guys so much for your attention. I hope you guys have a great day. And I will hop on to office hours in about 10 minutes. So if you need anything, I'll be over there.
Thank you.
All right.
Thank
Take
you.
care, guys.